All right, guys, our next section 11.4 deals with angles in relation to a circle. Okay, so you'll see when we get into our theorems that really we're talking about angles that could be in two different places in relation to the circle. Those bolded words as you see inside or outside of a circle. Pretty simple to comprehend. But first we give you one final definition of lines or segments that could go through or touch a circle, and that's a secant. Okay, a secant is a line that intersects a circle at 2 points. Now, that's very similar to a chord, okay? Within every secant line, you will see a chord. Okay, so this part here, if we were just talking about that, this is a chord. If we wanted to refer to the line that chord lies on, or if you see the chord, but instead of stopping at the endpoints, it goes on forever, this would be considered the secant. Okay? So within every secant line, you will see a chord. Okay? So in part of these, like if you look down here to the bottom in example 1, these are just chords. Okay? But the same thing applies. So like when we get the definition or when we get the theorem, you see that they continue on forever. Okay? But even if they didn't with these chords, all right, the same theorem would apply. The same things are happening. We have an angle, we have arcs, and you'll see what I mean when we get to this first theorem. Okay. So that first theorem says that the measure of an angle formed by two lines that intersect inside of a circle, okay, like angle 1. Angle 1 is representative of an angle formed by two lines that intersect inside the circle. So like angle 1, okay? What we need to realize with an angle that is inside the circle is that there are really two intercepted arcs, okay? So if we trace out the lines here, okay? And if we trace out the lines, what you'll see is that these two lines that form this angle basically form two arcs. They form one arc on the side of the angle, if you will, on the side of the angle that the intersection is on, okay? But they also form another intercepted arc, or something else that we would consider an intercepted arc, in this case, based on the theorem that we'll have. And it's basically the arc formed on the side of the vertical angle from angle 1. So the one on the opposite side of the intersection, we used to call those vertical angles, still do. This arc is also one of the two intercepted arcs, which lead us to our formula. The measure of the angle, the formula would be the average of the two intercepted arcs. How do we find the average of two things? Well, we add them up and divide by 2. So in this case, the measure of angle 1, okay, which is the angle of two lines intersecting inside the circle, would be equal to x plus y divided by 2 in this case. Okay? This angle is equal to the average of this intercepted arc and this intercepted arc, or in the case of this diagram, x and y. How do we find the average? X plus y divided by 2. All right, pretty simple theorem. Okay, but as you're going to see, we're starting to get angles that could be in different places in relation to the circle. Months ago, we talked about central angles, and then in section 11.3, we talked about inscribed angles. Now here's angles inside of a circle, and all of a sudden we have angles outside of a circle. The measure formed by an angle by two lines that intersect outside the circle is, well, again, we have two intercepted arcs. So let's trace out the lines that form this angle. Let's trace out the lines that form that angle. Let's trace out the lines that form that angle. Okay. And really, we have these two lines, these two lines, these two lines. They cut this circle into arcs. So these lines form this arc, but they also form this little one. Same thing here. We have one intercepted arc. We have another intercepted arc. We have one intercepted arc. We have another intercepted arc. Okay? So similarly to our first theorem, there are two intercepted arcs when two lines intersect outside of a circle. Okay? The formula for that, the angle would equal the far arc minus the near arc divided by 2. Okay. What do we mean by far and near? Well, we mean just that. Here's angle 1. Of these two arcs, which one's further away? X is further away. This is considered the far arc. The Y here would be considered the near arc because it's closer to the angle. All right. So in this first diagram, if I wanted to find the measure of angle 1, it would be X minus Y divided by 2. Okay. Look at the similarities between the two theorems. Could you guys see students getting confused on which one's which? We definitely do as teachers. Okay. Same thing for the second diagram. Angle outside the circle. Here's the far arc. Here's the near arc. And the same thing would apply here. We used X to be the far arc and Y to be the near arc and angle 1 each time just so we could have kind of a very simple theorem here. Okay? Now, just like always, okay, let's envision a problem that might come from this theorem. Could I give you the degree measure of the far arc and the near arc and ask you to find the measure of this angle? I could. Could I give you this angle and this far arc in degrees and ask you to solve for the near arc? I could still use this equation. It would just take different steps of algebra, okay, to end up solving that. All right, let's figure it out here. Okay. Example 1 says find the value of each variable. First thing we need to determine is the angle inside or outside the circle. That's what you want to ask yourself. And when we wrap up all of these different angles in our second day this week, all right, you're going to be asking yourself even more, inside, outside, on, or at the center. Okay. Find the value of each variable. Okay, this angle is formed by two lines intersecting inside the circle. Okay, so we want to think the average of the two arcs. Let's trace out our angle. Okay, trace out the lines that form the angle. Okay, and we see two intersected arcs. The one facing the angle, basically, the 46 degree, and then the one on the opposite side, or facing its vertical angle. Average of the arcs, add them, divide by 2. In this case, x would equal 46 plus 90 divided by 2 happens to be 68 degrees. Cool. Let's move on to 1b. This angle is formed by two lines intersecting outside of the circle. Okay. Now there are really two different ways to do this problem. We'll do the hard way first, then we'll talk about a shortcut in this type of problem. All right, here's my far. Well, let's use our colors. Here is, we're tracing out the angle. It's going to form two arcs. Here's the first arc, and here's the second arc. We have the far arc. We have the near arc. Okay, so let's use our formula. Okay, this is going to be an example of using our formula in a different way. So the angle, the measure of the angle, equals, we actually know the angle this time, far arc, which we don't know, minus near arc, which we do know, divided by 2. We set up an equation. We only have one variable. Well, at this point in our math careers, we should be able to solve any situation like that. What's the easiest way to do this? I would like to multiply both sides by 2 to get rid of that fraction. We get 140 equals w minus 110. I add 110 to both sides. I get 250. Okay. Now, as hopefully you might have seen before we did all that algebra and used our theorem, if it's two tangents that intersect outside the circle, well, it's only going to split this circle into two distinct arcs. There aren't four arcs like we saw here, 1, 2, 3, 4. There aren't four parts. There's only one part, two parts. Well, if the whole circle adds up to 360, we really could have just subtracted 110 from 360 and gotten the same answer. Let's move on to the next. This angle is formed by two lines that intersect outside the circle. Let's trace out those two lines. And you shall see that we have formed two arcs, a 95-degree arc and the Z arc that we're looking for. So, outside, so we're looking at far arc minus near arc divided by 2. So the measure of the angle, which we know, 20 degrees. Far arc, the one furthest from the angle, is 95, the near is Z. So far arc minus near arc divided by 2. Let's use some algebra. Multiply both sides by 2. 40 equals 95 minus Z. Let's subtract 95 from both sides. I get negative 55 equals negative Z. Divide by negative 1. Z equals 55. And last but not least, this is an angle formed by two lines that intersect outside the circle. Again, far arc minus near arc divided by 2. We don't know the angle. The angle equals far arc minus near arc divided by 2. Just do a little math. Not really a lot of algebra needed there. And that wraps up our secants. All right, remember a secant, new definition, a line that intersects a circle at 2 points. Within every secant, you will find a chord. Okay, and then we just got two theorems. Two lines intersecting inside the circle. You can find the measure of any of these angles by doing the two intercepted arcs divided by 2. The average of those arcs. When two lines form an angle outside the circle, we're doing far arc minus near arc divided by 2 to find that angle.